All right, good morning. The last note related to simple harmonic motion is about a phenomenon we call a resonance. Resonance happens, for example, when you're on a swing and you want to swing higher and higher and higher. In that case, well, you give an initial push and then more, again and again. So you keep adding energy into the system, but you don't do it randomly. Yeah? You don't do it when it swings in opposite direction to the motion you want to give. You do it, we call it synchronized, yeah, with the same frequency. Every pendulum, every system has its natural frequency. So if you're adding energy with the same frequency, natural frequency, you pump in energy more and more in it. And that's what we call a resonance. And sometimes it's a good thing. You can amplify the motion or signal. Sometimes it's not so good thing. Here, I'm not going to do it, but I strongly recommend to watch what will happen. So this is a snapshot from the middle of the movie. What's going to happen? Who knows? It's been many years ago. Right? But that's the reason why no platoon marches on the bridge. Because if they march, they might hit the same frequency and they might break the bridge. Well, fluids. So lots of stuff we know already about fluids because we use them every day. We drink them, we swim in those. And the question is related to experiment I'm going to show right now. Here I have a big, well, just in case. I have a beaker. And this ball now is completely in this reddish fluid. There are many different reasons it might be red. Food coloring, blood, red marker. So this is a case, and you need to choose your answer. There are several options for you for a free body diagram for the ball, which is on a string and at the same time in water, food coloring, so, and this part is not new. It's a standard application of our common sense to an object in equilibrium. The ball is in equilibrium. And as we know very well, if something is happening on the surface of this planet, there has to be force acting on it, which always points down and has a name, what? Gravity. Also, since a string is attached, and we know in physics touching means interaction, there is a tension force, and and we've got all possible answers except the right one. We just said touching means interaction. The ball touches water. Water touches the ball. That must result in a force. So if we count forces, it should be gravity, tension, and something else from the water. So we should have three forces. Do you see any diagram with three forces? No. So the answer is none of the above, right? So the true diagram should have three forces. And here, we actually can do an experiment running some numbers. Well, we don't really need to do numbers right now, but what we call this is a weight. This reading on the scale is equal to mg in equilibrium, so it's weight. We know how to change the weight. For example, we can walk into the elevator, press the button, we start moving, and the weight changes. But this is another way to change the weight. And you feel it every time when you immerse in bathtub. So if we didn't know what was happening, if we just were looking at this, we would assume this is the weight. So this number appears to be a weight. So how do we call it? Apparent weight. That's how we call it. But the force which is acting from this liquid, from water on the ball, that's what we call buoyant force. So the reason that apparent weight is not equal to the actual weight, mg, is the buoyant force acting on it. And well, let's just do it together. So this is the weight in the liquid. There's supposed to be force of tension acting on it. But that's a different tension now. That's actually what we call apparent weight. That's what we read. There is force of gravity. It doesn't go anywhere. But now, because of water, there's an additional force, and that is force we call the buoyant force. And from the Newton's second law applied to the equilibrium, which we have studied a month ago, we can write that magnitude of the buoyant force plus the magnitude of the apparent weight should be equal to mg. We can use it differently. For example, we can use it to calculate the apparent weight. Or we can use it to calculate the buoyant force. So if you know these two readings, so one should write the numbers. I don't see from behind. 11? So please write the number. 11 newtons. And now, any number? 3? 11, 3. So 11 is the actual weight. Yeah? That's what we call, well, 11 newtons. And this is the apparent weight. You say 3 newtons, I believe you. So the magnitude of that force acting on the ball from the water will be 11 minus 3, 7 newtons. See, simple. Now, of course, we need to, what?
Why are you saying 7?
I don't know.
8?
I wanted 4. It's still Wednesday for me, I don't know. I guess I'm that guy who is in a fog yet. Well, of course, we need to study properties of this force, and it's been done. Well, of course, the first person who did that was Archimedes. He was a genius. He studied lots of things. He didn't do much of the algebra. He actually used geometry a lot. But the experiment, which he kind of did, would look like this. All right, take this away. So we need any object which fits the beaker we can attach it to a scale. So again, this is the actual weight of it. Now what can we do? When the object is pushing on water, we see the level rises. The object displaces a certain amount of liquid. How much does it displace? Well, we can actually measure how much. This much. And now we can compare. Well, we see the new number. The difference between old number and new number is equal to the buoyant force. Right? On the other hand, we can measure the mass and the weight of the amount of liquid displaced by this object. We just need scale, which should work, and I have a backup. Put it on a scale, and I read about 190 grams. 90 grams, well, 190, 200, 0.2 times 10, 2 newtons. That's the weight of this. And we read the numbers, it's 2 newtons. And we can repeat this experiment again and again, and we see again and again that the magnitude of the buoyant force always equals to the weight of the fluid displaced by this object. For example, this is made of steel. If I get another one with exactly the same shape, but made of aluminum, so it's going to be lighter. But if I repeat the experiment, and if I collect again the water or read the number, I will see that the buoyant force again will be the same. So the buoyant force doesn't depend on the weight of this object. The buoyant force depends on the shape, the volume of this object, and the properties of water, of this liquid. So we can repeat these experiments again and again. There is one more, very similar to this one, but now with additional scale. So what you read here is the weight of this water, well, with the beaker, but we can neglect the mass of the beaker. It's thin. And if we attach a ball to the spring scale, we know what's going to happen when we will be immersing it in water. This reading decreases because water pushes up. What's going to happen to this reading? Well, it increases. And the reason, again, is simple. This ball pushes on the water, and that extra push goes down to the plate of this scale. But if we change, if we read the numbers, the change in the force here will be equal to the change in the force there, exactly the same. Newton's third law, actually. So this is how we can calculate the buoyant force using experiments. And this is what we saw what's happening on both scales, above and below. And of course, it works for any type of a fluid. Doesn't have to be water, could have been milk, oil, or something else. In all situations, it's all about diagrams. So here, please copy each picture and draw a free body diagram. If you do that, that's it, you're all set. If we talk about forces, we talk about free body diagrams, right? And I'm going to try to show at least some additional situations. And to do that, I need to switch. I'm going to switch now to the camera. You will not be seeing anything on the screen. Ta-da! Well, oops. Keep working. That's what I call good planning. So, we just saw a ball on a string. Of course, we also saw this when I started just put it in. And of course, the force depends on how much of water, of an object is in water. Now, number 5. Yeah. A floating ball. A ball floats. So, all situations describe equilibrium. In each situation, if you draw the free body diagram correctly, you're all set. Floating ball. Number 6, what's happening? I am pushing on a ball. I'm adding extra force to make the ball completely submerged. Instead of extra force, I could have been adding what? I could have been adding extra mass. For example, instead of a ball, I could have used a boat. In terms of a free body diagram, does it really matter if it's a ball or a boat? No. So if you draw a free body diagram for a ball, you can draw a free body diagram for the boat. If I'm adding extra force, the boat goes deeper. Instead of adding extra force, I can add in extra mass. It gets deeper and deeper and deeper and deeper and deeper. And eventually, there's a critical mass. If it's too much, it sinks. And now we get a case number 2. An object is sitting on the floor of the lake or pool. And again, you can draw a free body diagram for that situation. And let's see. Probably I need something taller. And maybe even more water. Oops. All right. Here. Floating. So, you're going down. No, I don't want to die. Don't worry. It's fine. It's a sensory deprivation bath. It makes it stronger and stronger. So, this, what? This is case number 3. Right? That's it. What is the difference between, let's say, a string and a rod? See, it says a rod, a string. How does it affect a diagram, if any? Oh. Yes, please. What is the difference between a string and a rod? All right. I don't know what you said. I couldn't hear, and I can't read lips, but you're right. So, let me move it away. For each diagram, we gotta use our common sense, our knowledge of properties, things like strings, rods. A rod cannot be compressed, so it is a support. A string, on the other hand, cannot support. It can only hold, right? So diagrams, right? Of course, there is a force of gravity acting on, well, every ball. Every ball. See, I say ball, and I want to write the word ball. And of course, there is a buoyant force because they all touch fluid, and the fluid touches back, and that buoyant force always points up against the gravity. Well, technically, yeah, it is acting on the ball. All right, now we gotta see if anything else is touching. And here, of course, string or rod, in this situation doesn't matter, or spring. Here, if it's a rod, it actually is support. It's like a floor. It's like a bump. So here and here we have a normal force. Here, of course, we have applied force due to the hand or an extra mass if we put in some extra on the top of it. Here, number 5, nothing else touching. So that's it, only 2 forces. And here, that's a string. So a string prevents it from rising to the surface. So it holds it. So that's supposed to be the tension. And that's supposed to point it down. Well, have we seen anything like that before, except dying ball? Yes, of course. Party. So what's happening here? Well, nothing special. You get a tank with helium, add some helium into, oops, to the balloon, and let it fly, and it doesn't. Why? Exactly. And we know what to do. We know that the amount of the strength of the buoyant force depends on how much it displaces. We just need it bigger, right? It has a hole. Okay. This tank is dying. Let's see if this will be enough. Yeah. Well, for a moment, only 2 forces been acting on it, gravity and buoyant. And turns out in this situation, size is large enough, so the buoyant force is stronger. It rises until it hits the ceiling. At the ceiling, we actually don't have a diagram here like that, but we could have. There is also normal force from the ceiling, which points down. Here, that's exactly this situation, a string which holds it. How do we know it holds it? Well, we know because if we cut it, it flies. That means the force was down, and now Yes. Yes, I don't understand. I don't understand what situation you try to refer to.
So for number 3,
Yes.
the string has tension because it's holding the ball from blowing up.
Yep.
So does that mean we're assuming that the ball is light enough that it would float otherwise?
Absolutely, exactly like in this situation. Exactly like in my, do you want to see it again? All right. Embrace yourself. Ooh. Displaced some water. Physics might be messy. So here what I want to do, I don't want to just cut the string here. I can just take it off. Oops. Oh, wait, if I can. I let it go. See? And again, we have to just use our common sense, our life experience. If you don't have such life experience, that's when we're not sure how to draw a body diagram. If we're not sure how to draw a free body diagram, that's it. We're not sure how to solve a problem. Any more questions? All right. This is where having a work-study student might be handy. So this is a strategy we can apply to solve any problem related to buoyant force, except we're going to learn one more equation very soon. All right. A 3-kilogram ball is immersed in water, and the apparent weight is 20 newtons. Calculate the magnitude of the buoyant force. Well, we know what to do. We just have to repeat the calculation we did like 5 minutes ago. 3 kilograms means the actual weight is 3 times 10, 30 newtons. Now, what does apparent weight mean? That we just need to remember is the reading on the scale. If we have a scale attached to it, that's what we read on the scale when the ball is in the fluid, and that's 20 newtons. And as we know very well now, so we have two forces here, buoyant and tension, and gravity is here. And tension, this apparent weight plus buoyancy, should be equal to mg. So the buoyant force will be equal to 30 minus 20, 10 newtons. How much water is displaced? Well, we know that from experiments, from the knowledge given us by Archimedes, that should be equal to, well, the weight of the displaced water in this case. And weight, how do we calculate weight? Well, mg. But now this mass doesn't represent the mass of this ball. This mass represents the mass of that water which has been displaced, collected in the cup. So what do we do? Well, this number, 10 newtons, should be equal to mass of the displaced water times g, which is also 10. Hence, we've displaced 10 over 10, 1 kilogram in this particular experiment. So it's actually maybe not water. Or the ball is very, very large. Yeah. Now, a different situation. It is a floating object now. The strategy doesn't depend on if it floats or attached to something. Still, free body diagram. But in this situation, how many forces do we have acting on it? Only two. Now it's only gravity and buoyant. So in this situation, the buoyant force will be equal to the force of gravity acting on this floating device. And it is 0.5 times 10, 5 newtons. How much fluid is displaced? We know that this should be equal to the mass of the displaced liquid times g. So 5 is equal to times 10. Turns out it displaces its own weight. Of course, it's natural kilograms. So when it floats, just floats, it displaces its own weight. Yeah, here it was 9.8, not 10. Now, of course, it should work for any fluid, and that leads to an additional physical variable quantity. We have to use density. One fluid is different from another fluid, or one object is different from another object by amount of stuff we can put in 1 cubic meter. If we have 1 cubic meter of water, it weighs 1 ton. If we have 1 cubic meter of, let's say, iron, it weighs 7,900 kilograms. So same volume, different mass. Some objects are more dense, some objects are less dense. So to demonstrate that property, we use a new physical quantity. We call it density. Well, in this situation, technically, we should call it the average density. It might be different inside the object, but normally it doesn't really matter. So the density, by a definition, equals this ratio. This is the mass of an object divided by its volume. But we usually use it differently, like this, because density has been measured for all important materials. For water, 1,000 kilograms per cubic meter, or we know from lecture 1 in grams, that's 1 gram per cubic centimeter. So please calculate this as an example. What would be the mass? So if you have 2 liters of soda, you want to calculate its mass, what number would you get in kilograms? Actually, it's not completely full, but I know the number. So when you calculate the number, please wave your right hand. So I would see how many people get the mass of a 2-liter bottle of soda. And it's a standard approximation for, like, if we have to solve a problem about soda or even milk, we usually assume that the density of that fluid is pretty close to the density of water. And density of water is pretty close usually to 1,000 kilograms per cubic meter or 1 gram per cubic centimeter. We can change it, of course. If we add some salt, or sugar. Ocean water is a little bit more dense than tap water. Bless you. Please wave. What's your number? Yes. 2 kilograms. Please clap. So we can use original units, kilograms and cubic meters. In that case, we need to convert liters into cubic meters. Or, well, first of all, if you know what to do, you do it. If you're not sure what to do, what do you do when you're not sure what to do? No. What do you do if you're not sure what to do? And if it doesn't help you, if something still is unclear, what do you do? Look it up, yes, which means ask. You can ask a person, you can ask your neighbor, you can ask Google. That's it. So 1 liter, what does it mean? Do you know what it means? So that's why you can't answer. So you have to what? Please ask.
How many cubic meters are in a liter?
I don't know. But I know what a liter is. It's a cube 10 centimeters by 10 centimeters by 10 centimeters. This is 1 liter. So now it's your choice. You can convert it into cubic meters like we did, or we can just use grams. And I want to use grams. It's faster in this situation. So the volume of this bottle, 2 liter bottle, is 2 times 10 times 10 times 10 cubic centimeters. And that gives this, all right? And to calculate the mass, we need to multiply 2 numbers. And if I use cubic centimeters, I would use grams for density. So 1 times 2 times 10 to the third, that gives me grams. Or now it's much easier to convert from grams to kilograms, 2 kilograms. So every 2 liter bottle is about 2 kilograms. 2. That's what I read here and projecting my vision to you. Do you feel it? Any questions? If you don't have any questions, well, this is the last equation about the buoyancy force. We know that it has to be equal to mass of the fluid displaced by G. This combination is the weight of the fluid displaced by an object. But now we can also apply this combination, a definition of density. And this is how people usually write the expression for the magnitude of the buoyant force. It is equal to the product of 3 variables. The density of the fluid, the volume of the fluid displaced by an object, times free fall acceleration. So if it's Earth, this number is 9.8 or 10. On the moon, it will be 1/6 of that. On different planet, it could have been different. If it's in outer space, no gravity, there is no buoyant force. But from practical point of view, we can rewrite the same equation because the amount of water displaced or liquid displaced or fluid displaced always equals to the volume of the object below the surface. So if we take this ball and we place it. Just let's see if you see what's happening to the level. Not really. Well, okay. Look here. Yeah. The teaching technologies could have been much better. Well, anyway, look here, don't look there. So in the picture, all you can see that the ball is getting in water, but see, the deeper it goes, the more water it gets displaced. And that volume of this ball below the surface is equal to the volume it displaces. Well, actually, this is what I also have. A boat. This is why it doesn't sink. It displaces a lot of water. And when it displaces a lot of water, the buoyant force is strong. Strong so it doesn't sink. I can actually do something different. So I can take, well, we can call it anchor. It's heavy, 2 kilograms. And what's going to happen now if I place this anchor in the bucket? What do you expect? Do you expect to see this much of the displacement? No. It doesn't displace almost anything. So buoyant force acting on this anchor is very, very small, weak. That's why actually it sinks. Right. So if I want to support it, I need to displace a lot of water, and that's what the boat does. You know. It allows to displace a lot of water, so it doesn't sink. These two equations physically identical, however, from a practical point of view, on the practical side, this is the equation which usually, well, easier to use because we can always see that part of an object which is below the surface. And then just do some geometry sometimes. That's it. Question. Please tell me what you think. We get the same ball you initially placed in water. And now, instead of water, we use glycerin. I don't want to do that because glycerin is sticky. So you have to use your imagination. How would that affect the apparent weight of the same ball? Would it affect the weight? No, the weight is always, actual weight is always m times g. But the reading on the scale to which this ball is attached depends on how strong the force pushing it up from water or from mercury or from, well, even air. We feel the buoyant force from the air acting on us. It's tiny because the density of air is about 1 kilogram per cubic meter. So it's 1,000 less than density of water. So do you think mercury would exert stronger, same, or weaker force than water? What do you think? Stronger? So if we have a force acting up, but stronger than before, that decreases the reading on the scale. Yeah. That's it. We don't really need an equation. We just need to use, again, our common sense. The reading it doesn't have to be mercury. If we have a strong force pushing up, the reading decreases, the apparent weight in this situation decreases. Well, this is just an illustration of the equation, right? We, of course, can do it algebraically. What do we do? Very quickly. It's alive. The new tension, that's what we are looking for. We need to compare it with the old tension, which is mg. And there's a buoyant force. And as we know, the new tension will be mg minus buoyant force. And as we know now, it will be equal to the density of the fluid times the volume, whatever you call it, displaced by an object, ng. So when we increase the density, we're subtracting larger number that decreases the apparent weight, that decreases that reading. Bless you. Now, please tell me what you think. Let me just give you a comment how this is related to this. So as we know, in general, we only have three options when we place an object in water or any other fluid below the surface, like this one, and then release it. It might rise to the surface. Aluminum. It might sink, or under certain conditions, it actually might keep floating inside, like a U-boat. So how do you think that depends on? And here we have, that's the density of the object. This is the density of the fluid. And we may have, well, first choice, equal, 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 or second choice, greater, greater, greater. Third choice, less, less, less. Fourth choice, greater equals less, less equals greater, or maybe something else. Ready? What's your choice? For example, to sink. If the object sinks, aluminum sinked in water, so the density of aluminum, the density of water, which is bigger. And wood floats, so the density of wood and density of water, which is bigger. Water. So well, technically, this is what we need to do, right? We placed it here and let it go. And there is, of course, a force of gravity acting on the object. And there is, of course, the buoyant force. And we don't know. It might be strong, equal, or not as strong. So let's just write it. Sinking, what does it mean? It means gravity is greater than the buoyant force. Floating, it means gravity is equal to the buoyant force. And rising, it means the buoyant force will be greater than the gravity. Here and now, at that particular instant. So we need to compare buoyant force V mg. And for the buoyant force, that's density of the fluid. And here, because it's completely in the fluid, that's just the volume of that object, G. And here, the mass of the object also is related to the density of the material it's made of, and the equation is the same. It's just density is different. Density of the object, same volume, same G. So you see the volume and G getting canceled, and everything is depending on this ratio. If the density of the fluid is greater than the density of the object, in that case, buoyant force is greater. It goes up to the surface. If it's equals. If density of the fluid is less, so density of the object is greater than, it sinks. What? Oh. I said density of the fluid greater than the density of the object. Yeah. Yeah. Free body diagram, again and again and again, gives away the answer. All right. A problem which is actually an experiment about floating. Have we seen this problem before? Yes, we have solved this very problem. It wasn't about a cylinder, it was about the ball. So, nothing new. Exactly same problem. Now we just need to move a step ahead. So we know how the free body diagram should look like. That's a cylinder. So it floats. It's not exactly vertical, but we can neglect it. But since we have devices we can use, we can measure everything we want to. Well, please, everybody, write down the numbers because you will have to tell them later. So I need a diameter. The diameter is about 7 centimeters. Now the whole length of this cylinder is about 17 centimeters. And now I want to measure this. Come on. How much of it's above on average? Now let's say 3.5 centimeters, between 3 and 4, 3.5 centimeters. How can we use this? Well, we can use this to calculate, well, there's a weight inside. Without the weight, it doesn't go practically in water. So I need to make it heavy. So we need to figure out the mass of that weight inside the cylinder using these data. That's it. That's all we need to do. And you have to draw a free body diagram for this floating cylinder. I think we don't need it anymore. And this free body diagram is no different from free body diagram of the ball floating. And that problem has been solved several slides ago. So far, no difference. Cylinder, we still have only two forces acting on it, mg and buoyant. And nothing else. So we know that in this situation, buoyant force will be equal to m times g. Well, we also know now that we always can relate the magnitude of the buoyant force with the density of the fluid, in this situation water, same g, and v. And here, where people make mistakes sometimes, is when you say v, you have to say that is the volume of the water displaced by an object, which is equal to the volume of the object below the surface. Object below surface. So this is this volume. If you say that out loud, you're all set. The rest is geometry. So well, first of all, since it's same force, m times g should be equal to density of water times this times g. So the mass of this cylinder with the weight inside should be equal to just density of water times that volume of the object below the surface. Since it's a cylinder, we know how to calculate the volume. The volume of a cylinder is area times height. Area is circular. So, and I'm going to use centimeters because those are readings. And if we use centimeters cubed, the density of water equals 1 gram per cubic centimeters. So density is 1. The volume of a cylinder, so area pi times diameter over 2 squared times height. Which height? Well, we need to multiply by the height of that part which is under the surface. But that part should be equal to total length minus the length above. So now I need you again to remind me the numbers. That is pi. Diameter was 4, right? Ah, 7. 7 over 2 squared. Total length was 17, and this was 3.5. Okay. So now it's your turn. You need to calculate what number? 519. That will be grams. And that is absolutely correct. I just put a 500 gram weight in it, plus 19 grams. That's it. Now, what is the density of this weight? Well, this, I think, brass, so we can Google it. It's, of course, on its own sinks. What does this do? This increases the amount of water it displaces, and that's why it floats. And if we calculate the average density of this object now, please calculate the average density of this cylinder. Not the density of the weight inside it, but the average density of this cylinder. What do you get? And the average density should be mass divided by the volume, total volume of this cylinder. The mass is 519 grams. And so the average density of this average should be equal to well, 519 grams divided by the total volume, and total volume should be equal to pi times total volumes, half of diameter squared times 17. We just don't subtract anything. So if you calculate this, what do you get? 0.79, 0.8. That's why it floats, like wood. A piece of wood has density less than water. That's why if I try to push it, it will rise as long as we let it float. Well, now we are actually pushing on this ball, same ball. It floated, and we want to make it completely submerged. So how does it change the free body diagram? We know how. We had that diagram. So now this is what I want. Oops. Now, of course, we still have the same force of gravity, mg. We still have buoyant force, different. But now we're also pushing some kind of additional applied force. And in this situation, what do we say? We should say that because the object is in equilibrium, Newton's second law for equilibrium tells us applied force plus gravity should together be equal to the magnitude of the buoyant force acting up. So if we need to calculate that force, this is what we need to do. Buoyant minus gravity. And now it's a technical problem. For the buoyant force, we should write density of water times the volume. The volume of the object below the surface in this situation is equal to the volume of the whole object. It's completely below the surface. So times g minus, well, in minus 0.5 times g. And this is not a cylinder, it's a sphere. So we got to go to equation sheet or ask someone, maybe Google, how would we calculate the volume of a sphere? Plus, since I'm using g here, that's going to be minus 5, and that's going to be newtons. I must use all units consistently, so I cannot use grams anymore for density. It has to be 1,000. 1,000 for water, 10 for g, and here I should write the expression for the volume of a sphere, 4/3 pi r cubed. So 4/3 pi. The radius is a half of a diameter, 0.22 over 2 cubed. That, well, someone should tell me the number. So please just calculate the buoyant force first, and then we subtract 5 of it. 0.22 over 2 is about 0.1. 0.1 cubed is about 10 to the negative third times 1,000. So it's about 40. I'm not sure the exact number, but it's close to 40. Maybe 41. 50? Yeah, because it's not 3, it's 3.14, and it's not 0.1, it's 0.11, so 50. Okay, I trust you. Newtons. This is the amount of that additional force. Now, if instead of pushing, we would be adding extra weight to it, more and more and more and more and more and more, what is that critical weight we should put on the top of it? Well, of course, in that situation, the picture would have been slightly different. Well, okay, that's a ball, that's additional weight. But this additional weight times, well, the mass of that additional weight times g should be equal to that additional force. So the mass of that additional weight would be equal to this force divided by g, which gives us 4.5 kilograms. That's how much we would have to add on the top of it. It still wouldn't be sinking. It would be floating with this weight on the top of it. But if we would add even one more additional gram, that's it. Any questions? All right. Please tell me, what do you think? Basically, the question is about the nature of this element. Do you think it's a rod or a string? If you think it's a solid rod, if we remove it, the ball should sink. If you think it's a string, if we cut it, it should float. So you have to make a decision what should be happening to this ball if we wouldn't be touching it with this element. And where is the answer to this question? Here. You know the density of the material of the ball. And we know we have answered a question about what should be happening if the density of the material of the ball is different from the density of water. This is why it is kind of handy to remember the number for the density of water. Do you remember? What is it? 1. In grams per cubic centimeter, 1. And this is 0.8. So now we need to compare two numbers, 0.8, 1. And now we have to make a decision. If we remove that element, what should be happening? Rise. That's it. So is it a rod or a string? String. That's important because that tells us the direction of that force acting. So now everything is clear. We just need to draw a free body diagram. Since it is a string, it holds it, so there's tension. And of course, buoyant force points up. There's gravity. Everything is in water below the surface. So now we look at this diagram, we know what to do. The buoyant force is supposed to be equal to mg plus tension. And the tension will be equal to the buoyant force minus mg. So for the buoyant force, we need to use density of water times the volume of the object below the surface. In this situation, that is the volume of the whole object times g, minus. And now we can use the same equation which relates density, volume, and mass, but it should be the density of the object times the volume of the object. So basically, that's what we're doing here. So 1,000 minus 800 times 4/3 times pi times, okay, a diameter over 2 cubed times 10. So someone has to tell me the number. And I'm going to move on to this question. If instead of using an actual string, we would use a spring, the spring would stretch. A string doesn't stretch practically. Yeah? So what would it tell us about how much it would stretch? Well, we just learned that there is a relationship between the magnitude of elastic force, spring constant, and that's what we call the elongation of a stretch. So the stretch would have been equal to the elastic force over spring constant. But in this situation, the elastic force is that force of tension. So that would be meters. As long as you tell me the force, I can calculate the stretch. So ten. Do I have a point somewhere? I don't know. 1047.
Yes.
You wanted to trick me. All right. So that could have been a very, very long spring, about 105 meters long. Well, I made up numbers, so it could have been an ocean. But that's how we have to solve this problem. You know what? If you so you answered the question, it would float. So if we remove it, floats. Okay. Any questions? We have described all possible situations. Yes? And eventually would float. So I'm just, again, thank you, thinking about what will happen next. My thoughts sometimes faster than my tongue. So, any questions? Well, yes?
Is the 105, would that just be the elongation of the spring?
Elongation.
After it's like a mission?
Yes. That's delta x. We don't know how long it is actually. It might have been very, very long or very, very short. We don't know. This is how much longer it becomes under that force acting on it. The Hooke's law. So again, the same slide tells us how we should approach any problem related to buoyant force. And draw a picture, etc., etc. Now, we're going to talk about pressure. Why is it important? Well, there is a difference. Here, you place a beaker on a scale, and of course you read the same number. It's the same amount of water. So the mass is the same, but mass distribution is different. And mass distribution matters. For example, in the winter, you know, if you remove the snowshoes, you actually sink in snow. And this is a traditional experiment. You can look it up online. It's called bed of nails. The mass of this person is distributed evenly. And that makes difference because if instead of bed of nails, you use only one nail, that's it. So this weight is equal to the weight of this rod. It's 500 grams. 500 grams. So the difference is the mass distribution, and that affects what's happening. Nothing. Sinks. So if this physical quantity is important, first of all, we give it an official definition, we give it a name, and then we study property of it. That's it. And to describe mass distribution or force distribution, that's what we do. If a force is spread around certain area, that amount of force divided by the area, that's what we call our precious pressure. Of course, I'll get one more minute. Of course, technically we should say that's an average pressure. But we're not going to use any specific pressures. Yeah. Force over area. This is a force acting on 1 square meter. That's what pressure is. All right, thank you. We're done for today. Now you can solve a lot of problems related to buoyant forces, which is a part of homework 3, part 2. Good morning. That's all right. You can take this all away. I'm done with this. Professor Duffy is done. Just a sec. Let's clean up a little here. There's one more. This. All right, now.